I'm very happy to see you all today. Happy New Year. And it's my big pleasure today to introduce our speaker, Franziska Emmerling. I'm sorry? There we go. She's head of the Department of Material Chemistry at BAM, so the Federal German Institute for Material Research and Testing in Berlin. She's lecturer also at the Department of Chemistry at Humboldt University in Berlin. And Professor Emmerling, she studied chemistry in Freiburg. She also obtained her PhD in Freiburg before she moved to Mainz for her postdoc, and then afterwards, if I see that correctly, to Berlin as a guest lecturer, first in the inorganic department, because she became head of the division in structural analysis at BAM, and then also head of the Department of Analytical Sciences, even in reference materials in 2017. And her research focused on understanding, if I see that in some shape, in fundamental processes involved in crystallization and shaping materials. So in particular, using mechanochemistry to control solid state and also develop new in situ and operando techniques. And we're very pleased to have you here today and to hear more about your recent work and see how we can basically tune and shape MOFs in exactly the shapes that we would like to have. Floor is yours. Thanks very much for coming.
Yeah, thanks a lot. Thanks a lot for having me here. It's a pleasure for me to show a bit of our work from the past years. I just saw that Darius joined, so that's a great pleasure. So that's our Polish colleague. We also have some nice publications. So let's move to the topic today. I want to tell you a bit about how we can use mechanochemistry to make also MOFs and other materials. But first, let me show a bit where I work. It is, of course, currently not looking like that. It is in snow, as you might have heard. So we are facing some challenging minus 10 degrees, or we have faced them. Today it's a bit better. But nevertheless, this is the largest. Let me see. So this is one of the largest science campuses we have. So similar to Munich, there's lots of things. University is around, and also, of course, our institution. You can see a bit of a round thing that might be interesting later on. So there is a synchrotron right around the corner, and my institute is lucky enough to have beam time there, and also an own beam line, so where we can really perform our operando and situ experiments in a very nice way. So yeah, and Humboldt University, you might recognize I can do everything by bike. So it's really not a big distance, and I'm teaching there. That's also where my students come usually from. Yeah, and we are an institute that belongs to the Federal Ministry for Economic Affairs and Energy. And yeah, our goal is to make materials safer and maybe also more sustainable. So I show you a picture of my group. We like to group around the symbol of our institute. You can see it's a bit of a mixture, highly diverse, old and young, and also many colors. And that's something we always, of course, look forward to, that there is also science is also always networking and spreading network throughout the world, which I think every one of you already knows. I will focus a bit on the work of these guys I show here on the side. And then we dive in about the things I would like to show you today. So as a bit of an outline, I'm not sure how familiar you are with the field of mechanochemistry. I will explain it a bit. Luckily, you can see here I stole a set from my kids at some point. There was a chemistry lab that nicely showed that usually chemistry labs look like this, and ours looks a bit like this. So there's more mortar and pestle around and mills. But nevertheless, it gives also rise to interesting reactions. And then I would move on to some examples from the MOF field, and also touching upon a COP that is also prepared mechanochemically. And then we look into a bit better understanding of these reactions that will then also help in the last chapter to guide a bit the upscaling of these processes. So let me first start with a short explanation. This is an explanation most of the colleagues rely on. So there's mechanochemistry, the branch of chemistry that looks into physical and chemical transformation of substances that are initiated by the effect of mechanical energy. So that would give rise also working in different states of aggregation, not only relying to the solid state, which would be tribal chemistry, if we want to use the proper term. So if we put stuff together and grind it, then usually we have a particle size reduction. Of course, we have a mixture, but we also create new active sites and fresh reactive surfaces, which is always a plus. So if you remember maybe older experiments in inorganic chemistry, then usually a grinding step was involved, and that's what we just keep on doing in our normal life. So what do we get from that? We get activation. We can usually observe fast kinetics. We often obtain new compounds, and sometimes you can also have improved material. And this is then again of interest in many areas where we look for application. It can be in the field of sensing, it can be energy transfer or other application. We are in desperate need of better materials or also improved materials, and this is also a way how we can get to them. So in this reaction coordinate, we can have the idea that we just have a different way of activating in our reactants, and then some of the reactions that might not be possible in solution are possible under these mechanochemical conditions. It is not a new thing, so if we look back in history, it might have been the first thing that people have done, undocumented, of course, but then later on also documented. You can see here some of the important reactions that were studied first, and if you look at the names, you can also see that there is prominence. So around, so Faraday and also Oswald were investigating mechanochemical reactions. They called it fly reactions. You see here Faraday is working with silver chloride, and then later on Matthew Carolier also investigated reactions by grinding mercury chloride and silver chloride, and then it moved on to metathesis reactions, and then at the end of the 19th century, mechanochemistry made it in a book, and that is usually the important step when something is really written down and also defined in a certain way. And then we have mechanochemistry, just like another flavor of chemistry, with a different kind of activation. And the definition I showed you before is the one that goes back to Heineke, who made the most accepted definition so far in the field. And in the present, I will show you, and also with other examples, mechanochemistry is really used in many fields of chemistry, organic chemistry, but also inorganic chemistry, and touches upon many different applications. So if we keep this guy here in mind, grinding two stones together, that changed a bit. So the thing we are now using, you can see here. So it goes from mixer mills to planetary mills. There's also a small mill we usually refer to that has a vertical geometry. But then there are also other types like drum mills, extrusion, and something called resonant acoustic mixing. And all these techniques are used in the broader community of mechanochemistry to generate new materials. So most of them you will find with your inorganic colleagues or geology colleagues. They usually use it to reduce particle sizes, but for us it is a reaction room. So usually we use those mills for different purposes. You see here, we have a type of milling vessel, and then there are also some balls inside. So usually the material we work with is a milling jar and different kinds of steel balls or zirconia balls, depending on the reaction we would like to investigate. Why are we interested in this technique? There are basically three important aspects. It's a sustainable method, and that is more and more evident that we need to rely on sustainable synthesis method if we want to keep the planet for a while. And also it allows us access to new and also known materials, and sometimes, as I said before, we can get better materials. So we have written two overviews here where we also showed that mechanochemistry really touches upon the principles of clean chemistry, reducing the solvent use, also leading to lesser energy input because they don't need to heat in the first place, and then also types of waste prevention. And it also touches upon the UN sustainability goals. This is a recent article where we showed in which field really mechanochemistry is key to synthesize materials with different application in a more sustainable way. For my group, we are interested in broader application of mechanochemistry, but what we usually do is looking into soft materials, so this is more in the organic regime, so organic chemistry, and of course metal-organic chemistry, and then most prominent porous materials with MOFs and then also POFs and so on. So yeah, moving on, we are not the only ones in the field that use mechanochemistry to generate MOFs, and I just leave that here as an impression. So I have two colleagues, Croatian colleagues, who are working. Thomas Fitches is working at the University of Birmingham, and we have Krunoslav Zarovic, who works at the Rudolf Boskovic Institute in Zagreb, and they are also very active in this area. So it is usually a good way to collaborate and also exchange ideas. We also have a common publication. So let's look at some of the materials we synthesize. I will start with an early example here. So these are phosphonates, metal phosphonates. We are very interested in for many reasons. So because of a very stable carbon phosphorus bond, you get materials that usually tolerate higher temperatures, and they come with a bit of a drawback, or came with a bit of a drawback in many cases, because it's not so easy to crystallize them and to obtain new materials and then characterize them. And it turned out, for instance, here, these materials, we were interested with a different degree of fluorination. They were not so easy to synthesize in solution, or not at all possible to synthesize them in solution. But it turns out that you can just make them super easily, just providing the linker. And then here, cadmium acetate as a salt salt. And then at room temperature, within 15 minutes, you get your crystal structure. Yeah. On the other side, what we obtain in the end of a mechanochemical reaction is, of course, not a shiny crystal. That is a bit of a drawback. So there is usually just powder available. And that means from a structure solution point of view, we have to solve the crystal structure from powder diffraction data. And luckily, that got a bit easier in the past years, basically because of the development on the protector side of the story in X-ray diffraction, but also because of many programs that help you to solve these crystal structures. So this is a main, I call it from ETH Zurich, always refers to that it's not so easy to solve these crystal structures, but nowadays you can also do it with a normal lab instrument if it's a bit tuned to fit the purpose. And this is what we usually do. So we solve the crystal structures if we don't have crystals and powder diffraction data, and then you see them as nice repel plots. And this is usually a way to have a good handle to solve the crystal structure. Okay, moving on from that example, it is of course also possible to have different linkers in one crystal structure. Here again, we were looking into metal phosphonates for the use as proton conductors. As you can see, so you would like to have different environments also for your metal, but also for the water molecules to bind on, and that is easily provided here using phosphonates. You can see we used again a very similar route. In this case, it's a cobalt acetate or iron chloride. You can really choose different metal sources. It is most of the time we go for something like an acetate, because then you already have someone to extract your proton. But nevertheless, you can see here the reaction is quite straightforward. In this case, it takes about 30 minutes, and you can easily make those in milligram ratio, but also up to gram. It depends a bit on the condition you choose in your mill. And here we also started to name our compounds in BAM 1 and 3 and so on. And you can see here the coordination environment in the different MOFs obtained here. And we also can see that we have something here that would be good for proton conduction. We have different channels where our water molecules could more or less hop along. So this is they are either structural BAM 1 and 2. And this is the other version. We then performed dynamic vapor absorption testing to see whether they would whether there is an affinity to water in these compounds, and this is a given. You can see a bit of the hysteresis. So the compounds are not super rigid, so there is a bit of the reaction to the guest molecules. And then in the next step, we also checked whether they show a decent proton conductivity, and without going into too much of the details, we could see that at higher temperature and higher relative humidity, there is a fairly good conductivity, and we could also derive the type of mechanism, how the protons are transported here. So you can see that it is an easy access to new materials, and these materials are then also directly useful for certain applications. So another example here is a recent work from Noelia, who is, I think, now in panic mode because she defends in 2 days. For her. Yeah, that's a collaboration with a Spanish university, and she did a part of her work with us and focused here on manufacturing metallogenic frameworks, again with mechanochemistry. In this case, it is ZIP9. You can see here again the conditions. It takes about 50 minutes, but is sometimes a bit of a process where you also look for highly crystalline materials. Just to make sure that it's not always an easy process, you can see there were several tries necessary to find the best recipe. So sodium chloride is the best additive in that case. And we are also not totally solventless. Sometimes there is a really minimal amount of solvent still necessary to make these reactions running or to completeness. But overall, it's a faster synthesis. We get the same structure like you get in solvothermal synthesis, and it takes just round about an hour, whereas in the solvothermal way, it's a bit longer. If we look here at the resulting crystallites, you can see that these here under mechanochemical conditions are more plate-like, and here you have more about rock scenario. And this is maybe the main reason why they also perform better when we test them for photocatalysis. I will show in a second. Just here to see what we usually take is X-ray diffraction, of course, to show that we have similar structures. And you can see, okay, there's a bit of an amorphous content maybe available, but the patterns are quite similar. So, and if we then use them for a photocatalytic testing, you can see here that is something we usually try in the first place, degradation of methylene blue in a so-called heterogeneous photophantom process. And you can see here that the degradation, so our mechaноchemically derived ZIP9 performs better and has a higher velocity in the molecule blue degradation as compared to the solvothermal counterpart. And this has to do, of course, with the fact that we have this different morphology, and also we have intrinsic effects that are derived throughout the mechanochemical process, but they are then beneficial when we think about application in catalysis. The structure stays stable in both cases, which is also a plus for cyclic processes. And just moving on in that direction, also, if you think of other electrocatalyst reaction, this is a more recent work where we synthesized here a nickel MOF compound, again on both ways, mechanochemically and non-mechanochemically. That's a bit of a strange acronym, but a bit the freedom of the PhD student to choose how to name his or her compounds. And we were looking into alcohol oxidation reaction in that case, but at the first test we were checking whether we have the same material. And you can see here from these data, you can also see that our institute has most of the techniques available. So we also tried to have a complete set of characterisation. So that's X-ray, of course, then thermothermically, and also XPS and XS, which shows us that we have in this case nickel in +2 state, and really there is not a big difference in these materials from a structural level, from the local structure. But if you look a bit closer again on here the SEM images, you can see that the mechanochemically derived materials have again a smaller particle size, and also this which in the end rise to a higher surface area. And then in the oxidation reactions, we can see here compared to the oxygen evolution reaction, and then we see the oxidation of different alcohols. Here in the oxygen evolution reaction, there is not big of a difference, but then when it comes to the alcohol oxidation, you can see that there is a pronounced difference, that the mechanically derived MOF is performing much better, and that seems to have to do with the particle size and also the higher surface area, so we have more accessible nickel active site, so the alcohol also needs to bind in the first place, and that makes these catalysts more efficient. Yeah, moving on maybe a bit to what has been happening in these mechanochemical processes. I already mentioned a few things like defects and other aspects like particle size reduction and so on, but it's not so super clear, or has not been that super clear, because as I said at the beginning, we're usually performing these reactions in an environment that doesn't make it directly possible to look inside or to understand the process a bit better. And this is the case, or has been the case for many reactions, so there was a limited understanding what's really going on, and especially we mostly rely to ex situ analysis, and then of course short-lived specimen or air-sensitive compounds are really difficult to track. And if we want to understand what is happening, really, we have to understand the mechanism, and that means we have to look inside our milling scenario. We really need to see what's going on throughout these reactions. So, and that basically means we have to change from a steel vessel to something that can be easily penetrated either by lasers, so Raman or IR, and then also X-rays. And this is how our setup usually looks like. So we have a milling vessel, and then we have a laser for our Raman detection. There's also a thermography to see how the temperature in the reaction vessel changes. And then, of course, X-ray X-ray diffraction as a key component to understand how the crystalline material changes, and that is only possible at the synchrotron. And with that knowledge, if we know really the mechanism, and if we can understand a bit more about the kinetics, then in the end we would be able also to control these processes, and then also scale the mechanical reaction up from a tiny little vessel to something much larger. So this is the setup again. there should be a movie. You can see here, that's how usually these reactions run. You can see something is moving up and down, which doesn't make it super easy for any analytics. Also, anything you would like to attach, it's usually ripped off sometimes, so there is a bit lots further. Here's mostly of the PhD student to make that run. So this is how it looks like at the synchrotron. This is not, that's why I usually show the sketch, because this looks rather messy, but that's the normal way to implement these things at the synchrotron. And we did different application and different steps to make these investigation easier and more profound to understand the reactions in a better way. I will show that with one example, another MOF we synthesized. And you can see here two sets of data. So in the middle, that's the X-ray diffraction. You can see in the bottom and on the top, EDAPs and the product. And then we look like on a top view, and you can see only the traces, similar to a barcode, what's going on in the reaction. And here on the right side, you can see the Raman spectra. So we can also monitor at the same time Raman and X-ray diffraction and see what's going on. So first things first, it's a fast reaction. It takes about 15 minutes for completion. And you can see here around about 4 minutes, they have the product phase. We could have stopped, to be honest. And you can also see the intensity doesn't change very much. So that's done. So the reaction is finished. If we look down here, then we see a period where we can see the starting materials. And then there is a formation of an intermediate. And then you see intermediate and product, and then pure product phase. The Raman data plot is more or less the same thing. You can monitor here the bands of the ligand, and you can see here the contribution of the final MOF that is formed, and it is more or less in the same regime. But Raman, of course, and X-ray monitor different things. In Raman, or in X-rays, we see the crystalline phases. Raman would also tell us a bit about what's going on in the amorphous regime. And here we can see Raman tells us that our ligand persists a bit longer, where we can see also from X-ray data that we have an intermediate compound with this stoichiometry. So both together really gives us a more clean picture on what's going on throughout the reaction. And this is also something that we tested with the first reaction we did, or the first publication we have with MOF and Mechanochemistry. You can see that's 15-year-old. And there the focus was, can we really make MOFs using Mechanochemistry? And then we compared to other synthesis roles. And as you can see here, so we milled about 25 minutes. Back then, my PhD student was more or less kicked out in the labs because it's also rather noisy if you perform mechanochemical reactions. So it was not optimal, to say the least. But it worked nicely. And a few years later, we tested this reaction also in an in situ investigation together with colleagues from Croatia I mentioned before. And you can see here a top view again, and this is the formation of H+1. And here we tested the influence of different solvents that we would add to our reaction. So it's only tiny amounts, it's few drops of solvents that make the trick. And you can see here, if you don't use any solvents, it takes a bit. So the reaction is at some point to completeness, but here, if you use methanol, for instance, that's a really fast reaction. Within 2-3 minutes, you have your final product. We investigated that a bit closer and then found out that it strongly depends on the solvent, which way the reaction takes. So we have a direct reaction with smaller solvent molecules. If we use longer solvents, then we see an intermediate formation. And if we use unpolar solvents, there is yet another intermediate. And if you investigate these mechanochemical reactions, then you know when to check for an intermediate. You can stop your reaction, perform a better X-ray diffraction pattern for instance, in the lab, and then we can also solve the crystal structure, which was interesting in that case because the paddle wheel we know from starting materials from the upper acetate and also from H plus is somehow broken for the sake of this intermediate, which is then reacting to the final compound. Yeah, maybe switching gears a bit and looking into covalent organic frameworks. This is a recent work by one of my PhD students working in CRC, where we focus on fluorine interaction. And here one of the very good fluorine interaction would be to have an adsorbable material for PFAS. And here you can see the reaction to form a Prof material. It's a 2D imine Prof that we generated here, and you can see the pores are just large enough to host the most prominent PFASs. And here again, I'll show you in situ data, which show basically that it's possible to optimize the synthesis condition. You know, a Prof are a bit boring when it comes to X-ray diffraction, or a bit, let's say, at least underwhelming. But you can see here that we chose different milling procedures, and then in the end also reached a higher crystalline material that could be then subjected to adsorption tests. And these investigations were done at DAISY, and it's also a lucky coincidence that there's a beamline that has a mechanochemical setup equipped for most of the time. You can also perform the reaction there. And then we demonstrated that this curve is quite efficient in terms of completeness and also time it needs for absorbing, in this case, one of the two prominent PFAS molecules in water. Okay, what I showed you so far is more in the 1 gram 200 milligrams regime of reaction, but we can also scale these processes up, and that's something that is of course of primary focus if you want to use it in an industrial level. And this I will show you in the last bit, where we look into how we can upscale these processes. I show here a bit the spectrum that we have in, let's say, at least somehow in our hands, and also the consideration that we usually take when it comes to industrial use and also upscaling of our reactions. So if we take a look at the upscaling spectrum, then it is clear that the interest is mostly in compounds that have a high chemical complexity and a lot of value that is added, as compared to something that is where the production volume is high. So that is clear that this is not the area where we compete. So more or less, this is the potential for mechanochemistry in manufacturing, and it's already done, for instance, for pharmaceuticals, and then for some catalysts. And in this area, this is really a big plus to introduce mechanochemistry also in industrial processes. And if you start in that direction, then there is usually the question, how can we come to larger batch sizes? And our material engineer friends, they usually have large mills around, so you can go to larger batches. We know a lot about the processes going on, so theoreticians can also help out here in this regard, and then you can translate from your little mill to a larger mill. This can be a bit problematic if your EDATs are not that inexpensive. Then you also have to think a lot before you try the larger batches. And the other way is that you go on for a continuous process. So, and there extruders are things that are, at least for the moment, of most of the interest. But just to show you, you can see here these colleagues from the MPI, they went up to make 3 kilograms of a co-crystal in this case just in a larger mill. Okay, going back to that, here what we focus on is using extrusion in our lab, and this is the next PhD candidate who will defend in February. Somehow they are all coming to an end at the moment. So Nikita looked into formation of SIF8. So we already knew from previous works that it is easy to make SIF8 mechanochemically. It's a 2-minute process, depending on how you choose your starting material. So usually we start from this basic zinc carbonate, and more or less Le Chatelier is in our site, so it drives the reaction towards formation of SIF8. So we also found out that you can just stir it and keep it and wait, and then you can also get SIF8 in the end. So it seems to be quite easy on this mechanochemical Prof. So, but if you want to translate it to a continuous process, there is some things we need to think about. So usually you have parameters like ball diameter, volume of reactant, frequency, and so on. And here we have other variables that we need to translate it to, so flow rate. We have something like a screw configuration, the extruder size, the size of the barrel, and maybe temperature as well, and that can be adjusted here. And of course, our tool usually is to look in the processes. So we want to use in situ investigations again, and that would mean that somehow we need to look into this here. So, and this is mostly steel or other materials. So there need to be a solution, and you can see here the exchange for transparent windows and different positions, and then we're able to look into the reaction. So a bit of ex situ information up front. So you can see here that you get an extrudate that can be washed then, and then it already looks like SIF8. You can sometimes see also side phase appearing, but nevertheless, this works quite nicely. And then we have to check it also in using in situ techniques in this way with Raman spectroscopy, and we can again monitor the bands belonging to the ligand and then to the final SIF8 compound. So everything is set up. Now we need to check to optimize our parameters, and you can see here that this is now in sketch mode. You can see the little crown indicating the best conditions. So first question, do we need the whole barrel length? Can we go with a shorter barrel? See, that looks okay. Conversion is not that high. Later on, we change from water to ethanol, and then you can see, okay, this is not bad. It leads to a higher yield, and also we can avoid the annoying side phases. And then there was a bit of more, let's say, optimizing in terms of ligand to metal ratio, and also a bit of speed in how the solvent is provided. But in the end, we were able to come up with a product that is really close to the commercial available one. And with this setup, you can end up with something like 3 kilograms a day in SIF8 production, which is quite a plus. Yeah, so that works. We get the material, but we also look into how green is that, and you can see here this radar chart where we compared a few other methods to our method here, and we were optimizing a few aspects. Of course, you would like to have a high surface area. We want to use the reagent in a stoichiometric value, usually at ambient temperature, avoid critical solvents, and so on. And then you can see the that's a longer comparison, and within our variables, our method seems to be one of the best, also better than some electrochemical methods, for instance. Okay, so you can see in situ is always the link to understand what's going on in these reactions. And you have seen the steel barrel. There's another chance to look into the reaction, which we tested in a more recent work. So this trajectory is okay, but industry would like to have the extrusion in place and also know what's going on. And here we tested with energy dispersive X-ray diffraction. This is a clever method if you want to penetrate the whole reaction vessel, and you also get a snapshot of your diffraction pattern at once, and you can really study things through containers. A bit of adaptation is still necessary. You can see that here, that is our extruder. You see the barrel here. We had to have a linear stage to address different positions, and we also had to exchange these steel screws by aluminum screws, so that there is a better chance to really shine through, and then we can easily monitor at different positions these types of processes. Again, synchrotron. This one looks not so messy compared to the other picture, but it's at the beginning. It's not in the middle of it. And then you get information about these processes, and just to quickly show you that here, for instance, we used ethanol and heated one area. You can see we get a highly crystalline ZA. In the end, if we change a bit the conditions and use water, for instance, as a solvent, we have this annoying side reaction, but we were also able to optimize it, or we knew how to optimize it up front. And you can see here under the optimized condition, it's a fast reaction. Within 25 minutes, you have your final compound. And this is for us a super interesting method because we get two types of information. We get the crystalline composition, we get crystalline size, we can see intermediates, which is sometimes not so easy with any spectroscopic techniques we use in the lab. And then we can really use that to understand these types of reactions a bit better. Okay, with that, I'm close to the end. I hope I convinced you that mechanochemistry might be worth a try if you want to make MOFs. It's an environment-friendly approach, and also opens pathways to materials that you cannot obtain maybe under other conditions. I think that the big step forward was the introduction of in situ techniques, which allows us to understand a bit better what's really going on during these mechanochemical reactions. And so there are different tools now available also for scaling up, which is then also fine if you want to include industry in these processes. Yeah, with that, I'd like to thank you for listening, and I'm very happy to answer your questions.
Wonderful. Thank you very, very much for this beautiful talk. I'm pretty sure there are many questions. You can either ask questions in the chat or just raise your hand. I see already Amedi asked a question with respect to the synthesis. If the duration basically, how the duration changes the basically the MOF structure, if that basically destroys the synthesis, how the influence is basically.
So if you mill for a prolonged time, whether then the crystallinity of the material would suffer, it depends. So we believe that under certain milling conditions, we have something like an equilibrium we go to, and then also the material is really stable and keeps the crystalline size. To be honest, in the beginning, I thought we are always ruining our materials, so that would decrease in crystalline size, but it keeps a certain crystalline size under these milling conditions. If again we would change the mill and have a higher impact, then there might be changes and also amorphization.
So is it then an impact of the screw size and the speed, how you do it, or the pressure, or how does that fit together?
It's a combination. So if we for the extrusion, it depends strongly, for instance, how you choose the sections you use. So there are kneading sections and conveying sections, and also whether you apply heat or not. under these mechanochemical conditions, there is a bit of, it's important, the size and the weight of the balls, for instance, you use. So it depends on the impact. And we know some reactions just they need like a constant impact to get started. So if you think about what's happening within the material when we introduce defects, and all of a sudden, let's say all the diffusion processes are more or are easier, and then the reaction starts. And we know of other processes that need a certain impact at the beginning to start. So changing a bit these things, for instance, changing using different materials or also increasing the size or the frequency can have an effect on the reaction.
Wow. Igunu had a question?
Actually, very, very similar question. By the way, the talk was great. Thank you, Franziska.
Thank you.
So I also know that, you know, ZIF-8 has amorphization process, especially when you apply ball milling pressure effects. So did you observe different transition states, something like metastable phases, or is it possible when you apply this kind of ball milling synthesis?
It is known in the SIP family, let's say, that there sometimes colleagues encounter changes. In our case, let's say you always have a certain recipe you start with, and in this range of input we provide mechanical energy input, we usually obtain only the pure phase. It can be that if you introduce a bit of a higher energy, that there's also a transition. I know also for other, let's say, polymorphs in the organic world, we know that it strongly depends on in the also milling time that you observe, for instance, formation of a more kinetically stable polymorph earlier on, and then later on the transformation to a more stable version. So that is possible.
Thank you. Thank you so much.
Wonderful. Viskas asked, same direction, basically, if there's any difference in terms of bonding between the metal and the ligand if you use mechanochemistry versus solvent.
No.
Nope. Okay.
It's
And
not
then,
from, let's say, from what I would then test is, or what we would use is basically XF and XPS, and they are similar. Yeah? You will have defects, of course, in the structure more pronounced than compared to polythermal material.
okay, because it's faster, basically. It's not as tick, tick, tick. Okay. Makeda, you raised the hand?
Yes, good morning, and thank you for the talk, Dr. Emmerling. I did have a question about the methodology for the milling. Did like various factors like milling time, ball size, or rotational frequency alter like the topology of the MOFs produced?
Yeah, it can alter the topology. Yeah, that can happen. To be honest, in most cases, when you use the solvents, or when you apply small amounts of solvents, you usually get it in a bit of a more cushioned regime. So then you can avoid a bit that there are larger differences within the topology. Yeah.
Okay. Are there other questions? Raise your hand. I have lots of questions. Maybe we start with a very small one. So you usually get small particles, nanoparticles, or smaller particles. Let's phrase it this way.
So if we think about crystallite size, if we derive the crystallite size from the X-rays, it is oftentimes around, I would say, 100 nanometers to 150 nanometers. So it is not nanocrystalline, at least again, in the regime we usually use. Our more inorganic friends, they use more often planetary mills, and then also other milling protocols. So in their case, oftentimes they would mill for 24 hours, and the result then could be more in the nanocrystalline regime, but with our, let's say, 20 minutes, half an hour reactions, it's usually of a higher crystallinity.
Okay, but let's say about 100 nanometer, more defectures, because there were also questions then if you use that towards catalysis, if that's more favorable if you use mechanochemistry because you have more open metal sites, for example, for catalytical approaches, or if you would go more to solvent-thermal. And then the same approach also, would you go for anhydrated metallic salts or hydrated metallic salts? It's always, I think it goes through the same question, I think.
So, yeah. So maybe for some of the catalytic reactions, we think that a mechanochemical derived materials are a bit fun, are a bit better because of course you have these smaller particles, you have usually higher surface areas, and you do have defects. So you have more possibilities for potential reactions to interact. So this seems to be the case for some of the reaction we are studying. Then they seem at least equal or better than the solvent-thermal counterpart. For the synthesis, if you think about starting materials, it turned out you can perform these mechanochemical reactions under dry conditions, so that's really dry powders, everything is dry. Then it often takes a bit longer, and sometimes also the crystallinity of the final product is lower. If you use hydrated salts, then you have an intrinsic, what we call liquid-assisted grinding, because at some point you set your water or whatever free, and then this will promote the process. So when it comes to solvents, that's another discussion also within the community, what these solvents do. We know from our organic synthesis that they often have an influence when it comes to polarity, and also that they can see differences in the local environment they would provide. So, because if you think about what's actually going on, you need to have at least some type of seed at some point to form a crystalline material. And we have a bit of micro environments where this starts, goes to a certain size, and then, let's say, takes over more or less. So that's the idea. Other colleagues also refer to it just like a thing to increase viscosity, let's say, so that they think it has no interaction. Yeah, but there are lots of studies that show that there can be a distinct influence of the tiny amount of solvent that you add.
Okay, yeah, thank you very much. Mohammed has a question, also a longer question. So you raised your hand, maybe ask it directly.
Hi, thank you for this interested talk. But I actually have already asked these two questions in chat.
Yeah.
One of them, how does the mechanochemical synthesize influence the effect formation of the MOFs or COFs? Another one, are the main limitations or the challenges of mechanochemical approach comparing with conventional method for purity and scalability of MOF and COF? That's all.
Yeah. So I think the defects I explained already a bit. So the crystallinity stays in a certain regime. So this is, as I said, around 100 to 200 nanometers. Long range order, if you compare the X-ray diffraction data, they look super similar. So this seems to be absolutely comparable to the thermal method. In controlling framework topology, what I showed you now, so the examples I showed you always end up in a steady state that is one compound. And at the beginning, at some point, I don't know where, let's see if I hold back. Yeah, here. You can see this is a bit what most of the mechanochemical reactions look like. Yeah, you have a induction period where you have this mixing, where you form the defects, and then reaction sets in. If you would stop, for instance, somewhere here, then you have, of course, a mixture of the starting compounds, maybe an intermediate that forms faster and something else. So it is always important to realize how long you should really mill, and that's what we do in the beginning. You know, when you stop after half an hour, and then you see, oh, there's some leftover reactant or whatever, and then you need to work from there.
Okay.
Yeah.
That's good. Okay, that's really nice. Okay, that's interesting. And how we can get this talk? It will be in the link in LinkedIn or some website.
It will be later on YouTube, but give us time. It has to be first
Oh,
brought in nice shape, of course.
okay.
Are
Thank
there
you.
other questions? Raise your hand. It's now your time to ask whatever I wanted to know. Maybe a last question, because you really highlighted so nicely that it's really sustainable compared to other more solvent-based approaches. Do you think, is there any limitation? Because usually what people try is to get rid of DMF or acetonitrile or whatever. Is there any limitation what to get, or I mean, just
So,
the beginning?
yeah, let's say, so as you have seen in some of my examples, there's still DMF. It's not that much. And also we need an activation step nevertheless in most of the cases, or at least
Some
some
solvent.
activation step. So there is that I think is with all the MOFs still the case. We realized, of course, that some of the if you think about some templating effect, I think that is still necessary in that case, but it can be tremendously removed if you think about the idea that you don't dissolve everything in to start with and then try to get rid of it. You know? There's an interesting work also where colleagues looked into a bit more of this. Let me see where this initial, I think in this initial reaction here, you know, forming mercury starting from cinnabar and using copper mortar. And an Italian colleague, she looked into that in more detail together with historians, and it turned out that adding liquids is the next step. So the dry reactions seem to be the more initial chemistry step. And it came later on, you know. And also now the first thing is, oh, I try to heat something up and dissolve it, and this, oh, we can also try to get it in a different way to react, is maybe it seems foreign to many of us, but seems to be more the first approach. So there's, for instance, if you think about first semester chemistry and detecting your ions and so on, the whole thing can also be done mechanochemically. So there is a way of doing that, for instance.
I see. Thank you very much. I don't see any further questions for now. Otherwise, maybe write an email. But let's
Yeah,
thank our speaker again for today, and thank you very much for joining. And see you then all together in about 4 weeks from now again, bright and shiny. Thank you very much for coming today. Thank you.
Thank you.
Thank you.